Alright, hello class. I have set up a green screen behind me and I'm a little bit flickery. Hopefully that's not distracting. I think I'm going to need, just shake those green screen flickers off. I think I'm going to need to get a better lighting setup if I pre-record videos. But today I'm going to run through the slides right here in front of me about Chapter 5, which I've already done during the live lecture, but now I'm going to do a bit of a recording. Again, you can fast forward through this, but please watch it all. The contents are going to be, we're going to talk about variables in programming languages, starting with concepts like names of variables, and then the attributes, other attributes that go with them, things like their address, and the concept of binding, when those properties get associated to the variable. Another attribute is going to be the scope, when the variable is visible, and its lifetime, which is the duration between when it's allocated and deallocated, and that can be different than the time when it's visible. We'll talk about different referencing environments for variables and name constants. And since a constant doesn't change, it's not the same as a variable, but they can be similar, and we'll discuss those a tiny bit. First, refresh your brain about this von Neumann architecture, where you have memory that stores both your program and the data, and then you have this constant loop, which is fetching an instruction, decoding an instruction, and executing that instruction in this never-ending potential loop. The key components being the memory and the processor. And variables represent for us an abstraction of the memory, right? And so instead of having to deal with addresses and imposing no interpretation upon the contents at those addresses, instead with variables, we're gonna abstract away addresses by giving things names and coming up with some kind of complex rules on how we manage those names, and also things like a type, which tell us which operations we can do with the data stored there, and impose some restrictions on the representations that we allow inside of a variable. Together with other attributes, things like managing when a variable is occupying a memory cell so that we can free memory up when we're not using it, or so that we can have multiple instances of that same variable in a recursive function call. And we'll talk about type systems that ensure that you're using types in a consistent way. To begin with, the first topic is something that affects people a lot when they're first learning programming, which is, what's in a name, right? I'm not going to quote Shakespeare. The introductory students to computer science don't come with this preconceived notion that you all have, because you've probably been learning Java, which is a C-derived language, and as such, it has case-sensitive names, much like the Unix operating system. But if you've ever programmed in Windows, one of the classic errors people will have when they transfer from Windows to Unix is they won't distinguish between uppercase and lowercase file names. And so you'll see a file name with a .JPG extension for a JPEG, or a .lowercase JP. And people who aren't used to case sensitivity, they'll just consider those the same. People, again, at the same notion when they're first coming into computer science, can find it very confusing that the word cat with an uppercase C and the word cat with a lowercase c can refer to completely different things in a computer program. There's actually no relationship that's imposed by the programming language or system at all between the names. In fact, we as programmers will often impose some sort of convention in how we spell things, but really uppercase and lowercase are completely unrelated in C-derived languages. But in languages like BASIC, uppercase cat and lowercase cat are the same thing. And so that's really a design issue, and you need to think about whether that's going to make it harder or easier for people to learn your language. Another key issue is, again, if you talk about language C, for instance, you can't name your variable for, F-O-R, right? If for some reason I wanted to name my variable for, or maybe I wanted to name my variable if, right? So those names, for practical reason, you have to imagine they're going to be off limits. Those words already mean something in the language, so they're reserved for those uses. You can't use them as a variable name. There's also other things which are keywords that mean something in specific contexts, right? So again, when you're designing a language, you get to decide which words are reserved and what are special words that might be predefined. So these keywords are predefined by the language, something like the printf function, right? Or actually no, you import that in C++. But imagine, or in C++, imagine the operators plus and minus, right? So these plus and minus operators have a predefined meaning, but you can actually overload those. You can change what plus means. You can change what minus means in a language like C++. So although it comes in with this predefined definition, sometimes you can overload them. And there are languages which would let you replace a lot of built-in things, and that can be good, or it can cause problems. It's a design issue you need to think about if you're creating a language, and you need to understand what the intent of the designers of the language you're using was. How did they solve that problem? Another issue for variables is length. Are really long variable names okay? And should they be necessary in order to use your program? Languages like C, the original C99, this changes over time as the standard adapts to what they expect the standard hardware to be. But originally it would be easier to keep your variables in fixed length arrays, so they said, all right, people can type as long an identifier as they want, but we're just going to truncate it to 64 bytes. With a null character, we have 63 characters at the max length of an identifier that distinguishes it from anything else. We're not going to compare the others. We're not going to really store the others in the image that we create when we parse this in memory. And even when you write it out to disk, once you've compiled the abstract syntax tree and you've translated it into a combination of machine code and then a table of names, so you know which function's implementation is where in the file, those names, those external names, they'll truncate them even further to just 32 bytes, 31 meaningful characters in the file. So that restriction lived there, and when you had libraries where the name of these functions was limited to 31 characters, you ended up being parsimonious with your file names and coming up with really weird names of functions in C++. If you look at the standard library, you'll see that there were a lot of abbreviations which were generally understood. But in more modern languages where the memory was cheaper and the libraries in use, hash tables and other things were built in, so it was easier to write compilers. These things, they've lifted that restriction. People weren't as concerned about the disk space or the RAM space as much, and your variable names can be as long as is needed. Languages like C++, it has a long history going back to C99, and a lot of different implementations of C++ for embedded devices and so forth, so they don't want to impose a lot of rules. That's one of the difficult things about C++, is a whole bunch of features are undefined. And so the standard of the language takes you to a certain point, and then you have to read up on the particular implementation you're using to figure out how it fills in these undefined parts of it. So again, length is an issue for identifiers that matters. And it dovetails into some other things that have to do with tooling. These slides won't talk much about tooling, but the tools that you use to develop code and the tools that people commonly use to develop code influence the way that designers prioritize these things. For instance, in the age of C99, you weren't likely to have autocomplete. You weren't likely to have all of these tools which you hit the first two letters in the tab key and it helps you spell long names. And so in fact, writing a really long name is difficult and error prone. But once you get to languages like C# and Java, C# comes into an ecosystem that already had Visual Studio, a very powerful tool with autocomplete, and same with Java and modern C++, where people favor really long names, but they also have tools to make sure that they've spelled them right as they're going. So that kind of practical concern helps, right? Another issue is the use of special characters in names, and it really has a lot more than you think to do with readability. If you look at a new programming language, if you've never looked at Java, or JavaScript rather, if you've never looked at JavaScript and you pull up a typical JavaScript program, you might go cross-eyed because there's dollar signs everywhere when people are using a particular library. I always forget the name of this library, but it's one of the main ones that people use in Java. In order to navigate the DOM, they have a special symbol. It's like a dollar sign. Oh, I tried to write, but I don't have a pen. Here we go, pen. It's like a dollar sign. Okay, there we go, a dollar sign like that. And then you can use that to search for items in the DOM, but this is just an identifier in JavaScript. So you got to get used to some of those. And in some languages, like if I recall BASIC correctly, a dollar sign meant the variable was a string. So in some languages, that prefix that you write means something, it imposes a constraint on the variable's type. Here, in Perl, all names begin with special characters that indicate the type. That's called Hungarian notation, right? So that really influences the name. Just by seeing the name, you know what type it is. It can make it harder to name things. You're coupling the type with the semantics there, but that can be done in a language. That's another design decision you have to think of. In Ruby as well, the name indicates its role. The @ symbol indicates that you're looking at an instance variable of an object, and the double @ is a class scoped. Variables in languages like Python, the underscore in front of a name means something by convention alone. In languages like C, underscore is reserved for things that might change in the implementation, so you shouldn't use it. But in languages like Python, it is the first character. It's okay elsewhere. Although the language allows it, the convention is not to do it. In Python, a double underscore will actually mean something by the language. It'll interpret that to be private. And in Python, private means pseudo-private. It just mangles the name for you if you use a double underscore. So, a lot of these things are meaningful in different ways, right? Another issue is, as we said, case sensitivity. I've already covered this. Anything based off of C, it's going to be case sensitive. Most of the languages that are popular right now, they can trace their ancestry back to C. But others may not. So if you end up finding yourself writing in a language which traces itself back a different route, it may or may not be case sensitive, and that's something you're going to need to think of. Your author claims this is worse. The issue for all of us in this class is we've already trained our brains to instantly be able to see the separation between words based off of the variable's case. So we've already gone through this indoctrination process, but you have to go back and imagine that this is your first time seeing a C-based language or C++ language if you'd somehow learned in BASIC the whole time. And now you're expected to figure this out. It's actually hard to even see this, right? So it is worse. It's just we're not sensitive to it probably anymore if we've been around C-based languages a lot. But it is an impact on readability. You do, of course, get over those impacts in readability through training. There are also in names. So in the programming language itself, you have certain keywords which help define stuff, and that can have a problem, right? So like I said, a reserved word like the word for or if, you don't want to use that as a variable name. Languages like COBOL, which I don't have any experience with, apparently have 300 reserved words, and it makes it really hard to come up with a valid name to use in the system. So, among special words, a reserved word can't be used as an identifier name. If it's not a reserved word, it could still be a special word. It can be something that's predefined. A keyword, it has special meaning only in certain contexts. And I don't have an example off the top of my head, but I do have the book. So let's take a peek and see if the book has for us a really good example of a keyword that is not a reserved word. Just in discussing COBOL, things like length and bottom and destination and count are all reserved words, and I think you can imagine that those are pretty likely words you would want to use in Fortran. Apparently, not in Fortran, in COBOL. In Fortran, a lot of the keywords can apparently be redefined, and the book doesn't really give you an example. I'm not a Fortran expert, but you know who is. If you guys get a chance, you can ask, oh my goodness, we have somebody on faculty who is an expert on Fortran, and maybe we can ask him what a special word that's not reserved is. But I'm going to move on right now. Dr. Fahrenberg, so you can ask him if you see him. A variable, really, as I said in this von Neumann architecture, von Neumanns are abstraction of how we deal with memory. So instead of just imagining we're moving through this large linear address space and looking things up only by their location and on a tape, we're going to instead imagine that we have names associated with these abstract memory cells. So a variable, right? And a variable has more than just a name. So we're imposing on memory these other attributes, such as a name, address, which would be its location in maybe physical memory, but in fact, as we see, we'll even want to abstract that just a little bit, because there's a lot of complex stuff that happens in there, paging in and out of memory, garbage collectors moving stuff around for us. So, but basically a location or an address, a value, the contents that are put there, the type, rules for what set of values are allowed, and the set of operations you can do on those values. The lifetime of a variable is really at what point do we reserve a chunk of memory to hold that value, and what point in time do we release that. And then the scope, which is overall it's a rule for when a particular variable is visible or invisible, inaccessible in your program. Again, names, not every variable, when you think about it, not every memory location has a name per se. It could be something that you've allocated and you only access it indirectly through links in a linked list, through pointers, through navigating a graph, or maybe you deleted the pointer to it and now it's just sitting there using up memory and you have no way to access it anymore, and it's a memory leak. So all of those things are in there. The address of a variable. Again, a variable can have different addresses at different times. During execution, you've got a garbage collector that's moving things around. You've got the call stack. And so that same variable can have different values and different addresses. Different instances of that variable can exist with different addresses. So, it's important to deal with that. Also, you have, related to that, the concept of an alias. So, you can have multiple names going to that same address, right? So in that situation, those two names are aliases, and it can lead to unexpected side effects where a change that's apparently being made to one part of your code surprisingly impacts another part of your code, right? And we don't like that. That's not orthogonal, right? So those kind of side effects of aliasing are undesirable. They can make it hard for the optimizer to optimize it. They can make it hard for the compiler to compile it. They can make it hard for the human being to predict what's going to happen. People won't expect that. Again, a really important property of variables that people use in order to make sure that the code that they write is correct is the variable's type, right? And there are rich type systems, rules about which types can operate together. And the beauty of type is you can, we dealt with that as an example when we were looking at static semantics. So with attribute grammars, you can scan through the source code, and before you even run it, you can kind of check to see whether it's consistent with the rules for these types. An integer must be added to another integer. You can't add it to a string, right? So if you can find those types of errors, then and you can force your program to be correct with respect to these types, then that helps you write correct programs, right? What we mean by a type is we're going to talk about a set of allowed values, and then a set of operations that are allowed on those values. So this is, together those form a data type, right? For integers, it's just 32-bit. Any combination of 32 bits is a valid integer, but then there's operations we can do. If we're going to add and we're going to subtract, and the particulars of those operations, they depend on our interpretation of those bits, right? Is it going to be sign magnitude? Is it going to be 2's complement? With real valued numbers, is again, it's your interpretation of the data as well. Is it a mantissa and a base? Is it a ratio of two numbers? Is it fixed point? Is the first 6 bits are the integer part, and then the next 12 bits are the fractional part? You've got to make those kinds of decisions in how you, and they're all coupled together there in those operations plus your rules for what can be represented. Then of course there's the value, right? So the value itself would be that what gets stored in the memory, right? Now when we deal with values, we can partition them into, let me just use my pen, we already talked about type, now we're talking about value. When we talk about value, we're really hitting those contents of the memory cell, right? But funny thing about values, it doesn't actually have to be inside a memory cell, right? So when we are writing an expression like x equals y, and we're understanding this to be an assignment, so we're going to take a value here and we're going to store it in the memory cell associated with the variable x, right? So we're going to store that value over here in some memory cell. What that means is this item here, which is on the left-hand side, all right, LHS for left-hand side, that is an L value, and for that variable we need its address. So whenever we talk about an L value, we're really talking about what we need there for that variable is an address. And then over here, you're on the right-hand side of the equal sign, you don't need an address for this, right? All you really need is the contents, the layout in bits, and that can be a constant, that could be hard-coded, that could be living on your chip somewhere in a register, so it's not actually out in memory somewhere, so it doesn't have an address. So it's to distinguish between those. So when we talk about R value, another word for that, when we talk about the value of a variable, another way to talk about that is really the R value. And when you hear people say L value, even though it says the word value in it, you have to think that they're really talking about an address. Okay, so let's kind of get that little semantic nomenclature issue out of the way. L value is its address. The R value is what we're really calling its value. It's the thing that can occur on the right-hand side of the equal sign. It's the actual set of bits that you're going to be writing in there. And then again, when we're talking about when we say the word abstract memory cell for a variable, your word might be arranged into 32-bit bytes, but you might have a double precision number, in which case the abstract memory cell is the whole thing, right? You also might have a value type struct, which it's as big as you want to because it's got all the different fields that you decided belong with it. And this whole chunk here we're going to consider to be sort of an abstract memory cell associated with that variable of that type, right? So again, we don't really care about the nitty-gritty of how it's laid out. Is it big endian or little endian and some of the stuff, because at least for the purpose of discussion in this class, we don't want to be specifically married to a specific hardware. So at the abstraction level of this course, it's an abstract memory cell, big enough to hold whatever we want to put in it. Right? So we've got all these attributes of a variable. We haven't discussed them all. Right? So what were there was a 6-tuplet, right? So let's just take a second now and remember what they were. We have name, address, value, right? Type. And then it's supposed to be 6, so what's missing? It's going to be lifetime and scope. Now we haven't gotten to those yet, because before we talk about lifetime and scope, we need to talk about another concept here, which is this process of binding, which is how and when you associate an attribute with an entity in a program, not just a variable. So there'll be other entities other than variables, right? But when do those attributes get associated to these things, right? So a binding is just the association of those attributes. Binding time is when that happens. and there are a variety of different binding times. And again, if you haven't already pulled out a piece of note paper, you should have, and you should have written down the 6 attributes of a variable. Again, name, type, value, name, type, value, address, lifetime, and scope, right? So you got those written down. Now I want you to get out your piece of paper and write down binding times. So what are the different binding times? You've got language design time, when you're writing the manuals, when you're brainstorming things, right? Language implementation time, when you're designing and building the compiler, really, right? Compile time, when you're reading in source code to translate it, right? So at that point in time, maybe some things become bound, right? For instance, you might at design time say, that the asterisk means we're going to do dereferencing of pointers, and the @ sign gets you the address of something, right? In a language like C++. At language design time. At language implementation time, you might decide that we're going to represent real numbers using the IEEE floating point standard, where it's base raised to the exponent, and then this is the first 16 bits, and then this is the second 16 bits. I don't remember if that's the way IEEE stores their floats, but it'll be something like that, right? Or you could say, I'm going to represent floating points where you have bit, 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 decimal point, bit, bit, bit. So this would be a fixed precision, right? So you might make that decision, and if it's not, I'm trying to write fixed and I failed, whatever. You might not make the decision when you go to implement it, or at language design time, right? So it's up to you. You might decide that integers are always 32 bits here, or you might decide that they're always 32 bits here. You might decide that they're 64 bits or 16 bits, right? So different languages have different notions of that, and you can make the decision at different times. At compile time, you can do things like you can figure out what the data type for a variable is in a statically typed language. So whenever we talk about a statically typed or static this or static that, right, you probably heard the word before. Really, static refers to anything that happens above this big red line I'm drawing right here, right? So at compile time, you can figure out the data type of a thing. At load time, remember you've got memory, and before your program can run, you've got little pieces of it that are pre-compiled living out on disk. These little static libraries, they have to be loaded into memory, and maybe this one is referring to something that's in this library. So it's at the time that this gets loaded that you can say, that name is referring to this object, right? So that kind of linking between, for instance, the name and the data might happen at load time. For static variables, again, they happen up here, that would be when the memory address would be associated with it for a variable declared extern in a C program, right? And then again, down here at the bottom, we've got runtime. And so runtime is anything that happens after, your entry point, right? So maybe this one has the function main in it. That thing gets loaded, and then your program counter gets set to main. And at that point in time, your program counter begins moving through your code. That is now runtime. You are executing your code, right? So that would be things like when you make an assignment to x equals new something, right? That would be the bindings that happen when you make a function call and it has to create a new memory address to store the local variables, right? So it would be binding those address at runtime. Okay. So again, what are the possible binding times? Language design, language implementation, compile, load, and runtime, right? So make sure that you got those kind of written down and you can remember them, because those are, when you get these little quizzes and exams, you always want to have the questions which are supposed to be the easy ones. Where, a hard problem is one where you have to demonstrate deeper understanding and really solve a problem, right? Easy ones are where you can just remember what are the 6 attributes associated with the variable. So at least don't lose those points, okay? So get those ones down. what are the different binding times? And you could say, I lost count of them. I'd have to enumerate them to remember how many there were. But you got language design, language implementation, compile, load, and run, right? So what are the 5 binding times, right? You should be able to come up with those. Now, broadly, as I said, there's a line that I drew, and anything above this line up here, that's called static. And anything below that line out here, this is going to be, you're going to see the word dynamic being used sometimes to refer to that. So when we were studying semantics, we had static semantics and the dynamic semantics, which we just called semantics. In static semantics, you had things like attribute grammars who could deal with making sure that you were using types correctly, right? And then we talked about dynamic semantics, and if you remember, dynamic semantics were predicting what would happen when you actually executed the cell, right? Given this input, what do you predict the output is going to be, or what do you predict the sequence of states it's going to go through? So those words that we used, just to make them concrete, or it's anything that happens before runtime and anything that happens after you begin running. Right? So before runtime, static binding. After you begin running, you've got a dynamic binding, right? So running through some of those things, we have one attribute that we might consider as type, right? So at what point in time does the type get bound? And this is actually one where a number of modern languages are making different decisions, and even within one language, it can happen at different times, right? So when you're thinking about type, you have to understand how is the type specified, and then also, depending on how it's specified, when does this binding take place? A static binding, there's a couple of ways that it could happen. So languages that use static binding are Java, for instance, and most C# and C++. These are all languages where the type is determined. The type is determined. You can analyze the code to determine what the types are. Right? For the most part, in C#. For Java and C++, always, right? So, but even when you're doing that and it's static, the type is determined before you run the code. Languages which aren't static would be languages like Python and JavaScript, where you don't know what the data types are going to be until you're actually running the code. These things happen; they're determined at runtime. There's no contract. There's no contract. There's no constraints embedded into the language and the framework that executes code in the language in order to make sure that types are being used consistently in some of those languages. Now, but if it is static, like your C++, like your Java, then you have the option of either explicitly saying what the type is, so it's a int x, and then I can set it equal to 3, or leaving it to be implicit. Maybe I just say x equals 3. Or maybe I say something like auto, let you decide, right? So if it's static, it could be the case that I'm telling you what the type should be, or the language system decides what the best type is to hold a thread, right? And as we talked about when we did these static semantics, in an attribute grammar, you can actually deduce, if there's an assignment statement, the type of the left-hand side must be the same as the right-hand side. Therefore, this type must be an integer if that is an integer, right? So those kinds of rules can be used to help you deduce what the types have to be. And in certain languages, you don't need to say anything at all, and it will automatically just implicitly determine the types. And maybe you have the option to put the type in if you want. Other languages like C++ has the auto keyword that was added to it, which allows it to do implicit type guessing, right? Type inference. Languages which don't use variables but have constants will also use the same sort of type inference process to deduce the type of their constants. They can still have type in languages like ML or Haskell, right? So an explicit declaration, as we say, is just a special program statement for determining the type. Two common patterns you'll see is the variable name and then a colon and then the type, or the type and then a space and then the variable name. So this is the way C++, Java, and those things do it. This is the way Pascal and Ada and even Python 3 lets you indicate the type, although in Python 3 the type is really just a comment. It doesn't mean anything. But still it uses a similar syntax. In an implicit declaration, you don't need to put anything there. Again, if I say x equals 4.7, then that means x is a float. And it is statically typed though. I can't later come back and say x equals banana or a, right? Because once I've done this assignment, the compiler has determined that x is a float. I can't, it has to stay a float, right? So it's not dynamic. It is static. It's determined before you run, and you have to be using it consistently or you'll get an error, right? Okay, languages like Basic, Perl, Ruby, they say JavaScript, and I'm not quite sure what they mean, and PHP provide implicit declarations. Some of these languages I don't have great familiarity with. Basic, you would say dim x equals 3, dim x, and as, and you'd give it a type, if I recall. So I'm not quite sure why they say they provide implicit. Maybe it's been a while since I used Basic. And then JavaScript I thought was dynamic. So maybe somebody who uses JavaScript can explain what the authors of the book mean that it uses implicit declarations. But it could be the case that there's a keyword in Java or something that I don't know. I am aware that in C++ you have the keyword auto, which will use implicit declarations, and I think you have the similar thing in Java as well. And C# has the keyword, I think, there. That'll do the same thing. So all of those will trigger it to do sort of implicit type declarations. There we go. C# uses the word var, and in that situation, it'll sort of implicitly determine the type if you've started it with the word var. Visual Basic, okay, if they said basic, maybe they mean Visual Basic 9. Basic is an old language. There's GW Basic, Basic A, it's been around for a really long time, and the version that I knew, I don't recall it using type inferencing, but here we do have it apparently in Visual Basic 9, where you have the context. ML is pretty famous for doing type inference, Haskell, F#. Again, are those really variables though? Because they're constant. But there we go. Dynamic type binding is used mostly. You're going to see it being used in very high level, what we call very high level languages, things like scripting languages. Ones where the flexibility has a priority over long compilation. You don't want to go through a long compilation time in order to see that it's correct. You're not concerned as much about the efficiency of being able to run the code either, right? Because there's a penalty for dynamic type binding, which is a lot of the type correctness stuff has to be done at runtime, and it can't be pre-computed or pre-done at compile time. So languages like JavaScript, Python, PHP, and if you use the correct keyword in C#, I can't remember what the keyword is for C#, but they're, okay, here we go. My book, dynamic. Okay, so the keyword dynamic in C# in front of a variable name will cause it to use, oh no, we can't see it. The keyword dynamic in C# will cause a variable to be dynamic, right? So you would say dynamic x equals 3. So it's there. And then, in languages that have dynamic types, you can have a situation where your list starts off, based off of this, the data type must be an array, right? In JavaScript. That would be an array in JavaScript. And over here, wait a minute, the data type here must be a number. I think JavaScript calls those numbers, right? In JavaScript. So your type changes between array and number as you go based off of what's assigned to it. That would be dynamic. The type change. You don't know what the type is associated with this name until you execute an assignment statement. And when you execute another assignment statement, that type could end up changing, right? As you can imagine, that can get pretty complicated. If you want to know which operations can be applied to this name, you have to check and see what's the current type, right? So it's very flexible, but it is high cost, right? Everything has to happen at runtime. When you want to print it and display it, there's different ways that you'd have to display a value if you know that it's a number versus if you know that it's a list. So again, all of that is there. And also, it's very difficult for a compiler to, ahead of time, detect errors or detect problems with the way that you're using values of different types. So again, you're sacrificing your ability to ensure that your program is correct, and what you're gaining is the ability to write code which is shorter, simpler, quicker to write, more adaptable, usable in more situations, but you can't guarantee that it's correct in all of those situations. So you're making a pro and con, right? If you're trying to write safety critical code, you might want to have that type safety in there to make sure that you're getting it right. If you need to get code out on Monday in order to have a feature delivered so that you can have a paycheck on Friday, or so that your company stays alive, you might like the appeal of getting things out quickly, the flexibility of dynamic typing. Or some hybrid combination of both. Maybe a piece of your product which you want to edit and change a lot is done in a high-level language, but the core functionality, which is highly efficient and you use a lot, stays in the low-level language. That's a pretty common way to do things. And that's a good reason for having more than one language in a project. But again, dynamic typing is out there, right? So that's types. Another thing is your memory cells, right? So one thing is, at what point do you get a memory cell, and how long do you have it? And so for that, we can talk about a lifetime or storage bindings, right? There's two phases that a variable might go through. The term allocation is if you imagine there's memory somewhere, and it can either live in a stack. Most programs that run and allow recursion have a stack somewhere, right? Not all programs, for instance, early Fortran might not. But then most programs will also have something out here which we call a heap, not to be confused with the heap data structure. It means something different. The heap is just a region of memory that is either free or used, right? So it's divided into these little chunks of used regions, and in between them you've got some free space, right? And you can sort of, as needed, your framework, your runtime environment, some library, is going to be able to scan through the heap, and you'll have marked certain portions of it as being already used, so you can't use them. And I say, hey, I need to allocate a new 8 bytes, and it'll come back and say, here you go, take those, and I'll mark them as being used, and there you go. So that's your heap, and it's got these little, it can get fragmented, right, as you use little bits of it. Very often in modern programming languages, you have a garbage collector out here, whose job is to detect keep track of who's referring to those memory units, and when nobody's referring to them anymore, the garbage collector will go back and toggle it to mark it as free. Right? But in addition, your garbage collector will actually recognize that you've got this big empty gap there, and it can move stuff around, right? So it'll move the memory around and then update the references so that they're pointing at the new location. So it's kind of like, if we remember that this is the scenario here, fundamentally, again, this is still a single abstract memory cell, even if it's moving around. Its lifetime begins when we say, hey, go give me some stuff out of the heap, and its lifetime ends when nothing refers to it anymore, and we'll either explicitly call delete, or the garbage collector goes back and marks it as free. Same thing in a stack. Again, the stack has memory cells. There's typically a stack pointer. When you make a new recursive function call, it'll go through and it'll figure out, okay, what are all of the local variables, and it'll allocate room for those local variables on the stack. And then when my function is done and it returns, it'll go through and it'll deallocate all of those variables off of the stack. So there can be different mechanisms for allocation and deallocation depending whether you're on the stack or the heap. But regardless, every variable is going to go from an allocation phase. It's going to be alive until it goes through a deallocation phase. And then in between those two periods in time would be the lifetime of that variable. Right? So there are several categories of lifetime. And so get your piece of paper out. Let me think about what I'll just name them right now, even though we haven't seen them all on the slide, right? So we've got static, which we can see here. Static means it gets its memory address before runtime, and anything that's static, it stays the same all throughout runtime, right? So static in English literally means it's staying the same, right? So a static variable is going to get its address before runtime. It's going to keep that address the entire time, right? So that would be static. Let me just name them and I'll describe them later. We're going to have stack dynamic, those variables that live on the stack. And for the heap, we're going to have explicit heap dynamic. So those are going to be the ones that we put on the heap, and then implicit heap dynamic. And then those are going to be things that are automatically put on the heap on our behalf, and we don't have to worry about them. So if we go through looking at static, right? So it gets a memory cell before execution begins. Anything that you declare static in C or C++, at load time, it's going to get its address. And that address is going to stay the same as the entire time the program runs. Again, same thing with Java. If you declare it as static, for instance, as well, it's processed before it begins. Your garbage collector might recognize it's static and put it in a special spot so it doesn't keep messing with it, right? The advantages of those static variables is there's some efficiency. For other types of variables, in order to get at its memory address, you have to first do some arithmetic. If you're on the stack, for instance, if you're on the stack and I want to know your address, I first have to look at the stack pointer, and really I have to add some offset, right, in order to figure out where you are. So there's that extra addition. Most of us aren't worried about like one operation every time you have to access a variable, but that exists there. So there's a little bit of indirection you'd have to do, and it can get even worse when you're dealing with garbage collectors and heaps and so forth. So in terms of, there's a little bit of a cost of that indirection. So you don't have that. So you get a little bit of efficiency when you have static variables. Even beyond that, you can get rid of that indirection completely by kind of going back and doing the find and replace through your code up front, so that stuff is just easily available. So languages that have like everything static would be the first Fortran, right? And it can be very efficient, right? If you're trying to shave off every millisecond for these complex complicated operations where you have to keep looking up the values of things, billions of times per second. So an advantage is efficiency. It can have an advantage when you're doing function calls, for instance, or other things. If you want to keep track of the history of a value between consecutive function calls, you might want to use static variables with a static lifetime. For instance, random numbers. And the string tokenization, the strtoke function in C++, these are all functions where the next time you call the function, its output depends on the previous one. This is difficult because they're not thread safe and they tell you not to do it, and in modern time we would use class-scoped variables instead of statically scoped variables, not class-scoped, instance variables of an object rather than a static variable for a lot of these things. But prior to that, your random number generator, right? In modern days, you'll create a random number generator object and you'll call random number generator.next. But in languages like C or C++, you would do something like srand or seed. You call a seed function to provide a seed. Let's call it S, right? And then that would set a static variable. You'd have a static variable, and you might call it seed. and you would set it equal to something, right? So really this is just setting it equal to something like, I don't know, 127, right? And then later you want to get a random number variable, so you call the rand function in C, and what is that going to do? I don't know exactly what it's going to do, but it's going to do something like this. It's going to set S, the new value of S, is going to get set to the result of calling some constant times maybe S plus some other constant, and taking that whole entire result and going modulo some other constant, right? So the idea is if you choose really big prime numbers here and here and here, then it becomes very hard to predict what your next seed is going to be given your previous one, right? So every time you call this, it's going to return the result of this mathematical expression, and you get all of these very unpredictable values. But the idea is the next value that you get depends on whatever the value that you had before, right? Each time you call rand, you're generating the same exact sequence of random values algorithmically, depending on the history that's remembered in this static variable S. Okay, so you can't do that unless you have some way to do static variables. Again, as I said, a lot of times in your object-oriented programs, you'll have a random number generator object, which keeps track of the seed, and you'll keep calling a method. But we're not there right now, right? So when you're just looking at languages like C, for instance, or C++, but you're not worrying about objects yet, then you end up wanting to do static storage. And there can be other scenarios where you might want to do that as well. The other type I mentioned is stack dynamics. So when you're doing procedure calls and the memory associated with a variable is relative to the stack pointer. Right? So here you have a function, and in that function you have a local variable. And that local variable can either, it has like somewhere in your code you say x equals 3, or int x equals 3. In the original, like C, you'd have to put all your declarations at the top of your code, because all the declarations all have to happen first so that it makes room for them on the stack. But other languages, it might automatically scan it during parsing and pre-allocate space for them on the stack, or you might have languages where it doesn't put room for them on the stack until it encounters that declaration. Regardless, the declaration is elaborated at some point, and once it becomes, as it becomes elaborated, you have to make room for it on the stack. So things which are stack dynamic, generally all of their attributes, it says all attributes except address, and of course value, would be statically bound, put on a stack. The local variables in C programs which are not declared static, local variables in Java methods which are not declared static, those would all be stack dynamic. They get their address, the primitive types in Java, not the objects, right? While the references themselves go on the stack, right? Those are all going to be examples of stack dynamic things, right? So again, you've got a stack, boom, you've got a stack pointer, you've got some local variable x, some local variable y, those get elaborated, they get room on the stack, right? It allows recursion because that same variable can exist again at the same offset in a recursive call. So you have another x and another y on the stack in a recursive call. So that's nice, right? So the variable lives as long as this function is active, and when the function returns, it gets deallocated, right? And the advantage is you're not using any memory until you make the function call, right? In a language like Fortran, a local variable of a function, the original Fortran, not modern ones, the original function, once you declared a function with a local variable, those were all static. So whether you called the function or not, it was using up memory, right? Whereas in modern languages, those local variables aren't using memory until the function's called. And furthermore, you can actually keep calling that function multiple times without clobbering the data that was in the local variables, right? Because instead of just having one static copy of the local variable x, you get multiple copies on a stack. And those stack semantics works well. Again, you have to use indirect addressing to figure out the memory address of a local variable x. And if it's not declared static, then your subprogram won't be history sensitive. Again, that's a pretty weak disadvantage because you can record the history by passing parameters, or in object-oriented programs, you can record the history as an object attribute, which is really just passing it as a parameter. Okay, so again, so we've got things that live on the stack dynamic, things that are kept globally constant the whole time, the static variables. Very good. And so what else do we have? We have things that are put on the heap, and so you explicitly you can dynamic means they're given an address at runtime, and of course it's living on the heap now. And these are things which I specifically put on the heap by saying new in Java. And for those of you who know C++, you can also say delete to pull it off of the heap. In Java, you can call finalize, but Java doesn't really have a way to pull it off the heap because the garbage collector does that for you. Unless Java has features I don't know about. But in C++ you would use delete to pull it off the heap. And it's up to you as the programmer to decide when it goes on and when it goes off. It doesn't happen automatically when a function returns. It doesn't happen automatically when a function's called. When you have to explicitly call new or delete. So those would be explicit. Explicit in English means you specifically say it, versus implied. Right? So explicit means you've got to say it goes there using new. The advantage is it gives you dynamic storage management. The memory can last longer than a single function call. The memory can continue to be there and available. You could return an add pointer to it, or you could add it, you could modify some stuff to somehow keep track of that memory, but it continues to live there until you decide you don't need it anymore and remove it. So it's all up to you. It's under your control. The disadvantage is it's inefficient. You need some process to scan through the heap and figure out, oh, this one's available, or this region is not. So you have to have some process of finding it on the heap. And then in order to access it, you have to have a pointer to it, which you can process. So again, you have to take this thing and you have to do a little bit of indirection in order to get to it. When they say unreliable, it's conceivable in many of those languages that your pointer is going out here someplace it shouldn't be. And you don't really always have a way to know that. So you can accidentally try to access memory you shouldn't have, or you can take your pointer and change it so it points somewhere else. But this is still marked as being used on the heap, and so you can actually run out of memory because you had a memory leak. So both of those sorts of things, especially in C++ programs, are examples of what could cause your code to be unreliable in that situation. So, and why is it unreliable? Because explicit means that you as the programmer make the decision. And whenever I give you, the programmer, control, I give you, the programmer, the ability to make mistakes. And you will. We all do. If the framework or the system can take care of it for us, then there is some hope that the framework is better at this specific task, as long as all the constraints and rules are followed, than the human being would be. An example of a framework taking control of this completely would be implicit heap dynamic, where you don't say to go out and make something new, the framework figures out that it should. So in certain languages like APL, I do not have experience in APL or in Perl, this is automatically done for you. In Python, you never really say new, right? You would say x equals, and if you want it to be a new list of numbers, you'd say 1, 2, 3. What does that mean? The Python interpreter decides to go out and allocate space for this list for you. You don't tell it to. It just does it when it's needed, right? And you also don't tell it to free the space either. It figures out when to free the space. So the entire thing is done on your behalf, right? So there is no explicit keyword to go out and do it. That would be implicit heap dynamic. It is most often used in languages which also have, they're completely dynamic, for like a very high level language. It can be very inefficient. basically all of the attributes end up being dynamic, including the type. So like I said, you'll have dynamic typing. You also will often have implicit heap dynamic storage. And you lose a lot of ability to detect errors. When the programmer has to be explicit about stuff, or when the programmer is restricted, then it's harder for them to misbehave. As a general rule, it becomes harder to actually write code, but it becomes more likely that the code that you wrote was intentional, right? So there's a trade-off there. So again, in a lot of these higher level scripting language where the focus is on flexibility, getting it out quick, getting it out fast, but it might have unintended behaviors, aka errors, then if that's your priority, then you go with these dynamic languages. And it sounds like that shouldn't be the priority for anyone, but in fact, in reality, very often the driving concern is the speed to market. Right? So if it's not going to hurt anybody, right? Safety would tip things the other way. When safety becomes a concern, you don't want to make an error, right? But if an error means that somebody loses an hour of work, again, they'll be irritated, but they'd probably still rather have the product, right? So, and you got to figure out where that line is, right? So, and you can see when you're using tools where different people draw the line, and maybe you disagree with them. Okay, so another attribute here, we've got, we just really talked about lifetimes. And again, lifetime, you have a variable, it gets allocated, and it lives until it gets deallocated. However, it could be the case that a variable gets allocated at some point. Maybe we call this variable x, right? And maybe I call a method, all right? And this method has another variable named x, and that shadows the previous one. So you can't, if I'm in this method and I want to refer to x, I get that variable, not this variable. So in fact, that lifetime can have these little holes in it, right? So the scope of the variable x, this variable x, would be the period of time it's visible. It would be here with a scope hole, and then it would continue through here. And there can be other reasons that scope of that variable is hidden, right? It's up to you when you design a language. If I write a method, can that method only access local variables to that method, or can it access global variables as well? Right? If you allow it to go back and access the global variables, it'd be fine. Otherwise, whenever you invoke a method, that global variable might be hidden. I don't know. It's up to you, right? The scope rules of language determine how these names are associated with them. Term local would be a variable who's declared and its scope is the lifetime of the active function. Non-local variables, they're not global, but they're declared in some other unit of code, perhaps that contains this function. So languages which let you have nested scopes might have non-local variables, and then of course global variables are kind of your top level variables for the whole thing. So there are two different major categories of how you manage scope that languages used. There's static and dynamic scope. When Lisp was first created, they used something called dynamic scope. And I can't think of another example where anybody would choose to use dynamic scope. And so first we'll explain what static scope means, and you'll be like, what else could there be? And then we'll talk about dynamic scope, and you'll be like, that's dumb. But it was easy to implement. So, and it's actually easy to accidentally implement too, I think. So static scope is where the scope is can be determined just by looking at the source code, right? It doesn't depend on runtime. Static, right? The idea is all you have to do is figure out where the declaration of a variable is, and you can figure out what its scope is. Where when we think of a scope, we really want to think of a set. You want to imagine that there is a stack of hash tables. That's the way I like to think of it, right? So you've got some sort of a stack of hash tables, and each one of these hash tables here might represent its own little scope. And based off of the declaration, you can figure out where it lives inside of the stack of hash tables. All right, so if I'm trying to figure out, so at the global scope, maybe I have X and Y, and then a containing scope, I've got Y and Z and W, and then in this inner scope, I've got W and let's say Y again, right? So, okay, if I want to look up Z, what do? I look at the current scope, and if I don't find Z, I'll move up to its parent, and aha, I found Z. So that would be this, what I mean by Z, right? So, where does this list of containing scopes come from? Well, you can determine it just by looking at the source code, not by running it, right? So an example is every single program you've ever written, right? You can look inside one curly brace to another curly brace. Every variable declared in there is part of that curly brace's scope. And then if you have a containing set of curly braces, any variable declared in there is in that curly brace's scope, right? So really often the nesting of the blocks of code in a block structured language usually corresponds to your scope. These things that you'd look back, those are called static ancestors, and they're usually, you can think of them as the containing scopes, right? The outer curly braces in our C-based languages. Ancestors, parent, this is the current scope, right? Some languages, like Python or like JavaScript, allow for nested subprogram definitions, which create nested scopes at runtime. Things like Ada, JavaScript, Lisp, Scheme, Fortran, F#, and Python. Languages like C++ don't. Java, I'm going to have to walk that back. Languages like C++ didn't, and Java didn't, but at some point in time, both of those languages introduced lambda functions and support for higher order functions. And although I don't know the details of how they did it, it seems to me at the time that they did it, which was after 2015, at the time that they did it, they must have also somehow found a way to allow some sort of a nested scope, right? A nested static scope. We can look at some details of those, especially when we talk about Python, right? However, you can determine the scope you can determine the structure of this scope tree statically, right? So they're still statically scoped languages, right? So one thing about scope is a variable can be hidden if there is a closer variable with the same name. Again, if you imagine what I drew, if this is your innermost scope, and it's a hash table, and you've defined X and Y, and you've got scopes further up, and maybe this scope over here also had, let's say, a Y and a Z. If this scope has an X, and I'm looking up X, I'm always going to start in the innermost scope and keep looking at the parents to find X, right? So if I'm looking for X, I'm going to find this one. I wouldn't find an X that's out here. If I'm looking for Y, I'm going to find this one. I'm not going to find the one that's out here. If I'm looking for Z, it doesn't exist. So then I'll look there and it doesn't exist, and I'll find it here, but I wouldn't find the Z that it was in its parent scope. So effectively, this Z shadows that one, right? So that's what it means when one name kind of shadows another one, right? Because of that, you end up with scope holes when a variable is hidden by a closer variable of the same name, right? Again, to help make these concrete, I kind of jumped ahead. There's this term of a block, and Algol 60, really old language, kind of introduced this idea, and we've loved it, and we've stuck with it almost ever since, right? So the idea of a block is it's really a way of creating a static scope inside of a program. They're a region of code, and they're delimited somehow. It could be between words begin and end. It could be between an open curly brace and a closed curly brace, or if you're Python, it could be between a colon and an indent, right? So you have a colon, and then everything which is indented the same level is part of a block in Python, right? So depending on your language, you have a different way to indicate blocks, and those blocks tend to define their own static scope. So for here, we create one scope with this curly brace, and another nested scope with that curly brace. And then of course the file itself is a global scope, right? So for this piece of code, you kind of have your global scope, and we have no idea what's in it. And then inside of that global scope, we have a scope for the sub-program. That's this curly brace right here, right? And in there, you have a variable called count, right? And then here we have yet another scope for that while loop. This one, you might want to use numbers to indicate the scopes here, right? So this is 1, and this is scope number 2, right? And then in there, we also have a count. And so at this point in time, when we execute that code, the current scope is this one. And we want to look up count, we're going to find that version of count. It's the one that was elaborated right there. Okay? So that's kind of this whole concept of a block-structured language. You can nest them arbitrarily deep. Scopes don't just correspond to function calls. As you can see, a scope can correspond to really anywhere that you see a curly brace in a language like C. And in fact, the contents here, you can actually put declarations that go into that scope, and at least in C++. I'm not sure, I don't think they do in C, right? So you got to know those rules. Okay, so in addition, we have functional languages, which also have, if you remember, we used the let construct, or also lambda functions in functional languages. And those also create scopes, and you can nest let constructs as deep as you want, right? We used let. We often used a square brace here, but it's the same thing. We would have a name, and then an expression that was stored there, a name, and then the expression that was stored there. And then finally, after this brace, we have a bunch of code that could use those variables, and then finally we would close this parenthesis. Right? So this parenthesis and that parenthesis are matched up, and then this parenthesis and that parenthesis are matched up. But in here, you've got code that can use all of those names, so those are inside of a scope. Of course, you don't want to call them variables because you can't write to them, but you do have every other property other than an address associated with those quantities in here. In languages like ML, it's the same. Keyword let, name value, name value. Again, these aren't variables, they don't have addresses, but they have all the other properties, so they're very similar, right? You get expressions. In F#, I don't use F# very much. You just do that. I think you only get to do one assignment at a time in a let in F# apparently. I don't use it. I'm going to imagine that you have to repeat this for every variable you'd want. So you do let until it ended. In other languages, the rules for when a variable first enters the scope can be different. In C++ and C99 and Java, the variable enters the scope at the same line as its declaration. right? So it's actually not in the scope for the entire block. It sort of enters the scope when you hit its declaration. In C#, no matter where it's declared within a block, it enters the scope at the top of the block, and we saw that when we were debugging C# programs. Now, even though it enters the scope at the top of the block, you're not allowed to use it until after you've declared it in C#. In languages like C++, Java, and C#, you can actually declare a variable inside of a for statement, and it belongs to the scope of the curly braces that follow the for, right? So you can say for int x equals 3, something here, something there, and then a curly brace. The x belongs into that scope, right? Okay, the x belongs in the scope that goes with this block of code, right? It doesn't go into the outer scope. No, it goes into the inner scope. There was a classic bug in Visual C++ 6, and you might see some old code written for that, where it put the declaration here in the wrong scope. And in languages like C, so C is not listed here, I believe it would put it in the containing scope. So it's important to keep that straight for those constructs. Some programs allow you to have global variables, C, C++, PHP, Python. You can have variables that are free outside of anything else at the top of the file. And those are going to be, we can call them global. So they're module scoped in Python. And in C, they're global. So they don't just live within that module, they live across the entire program unless you declare them static, which in this case means module scoped. They reused the word static to mean something completely different at the top of the program. So that's just a weird thing about C and C++. So those ones let you have those global variables that are outside of any function or any class. And the languages C and C++ allow you to partially bind attributes to a name using something called a declaration. So in order to, for instance, if you want to access a function that's defined in another library, you still need to inform the compiler that's compiling my piece of code what's the return type of that function going to be, what are the parameters of that function going to be, what are the data, so a lot of those different things you can do in a declaration. So in a C program you can say extern int x, maybe that's an array of things. Right? I don't allocate space for that array, but I do know that it is going to be an array of integers. So those properties get determined when I'm compiling my C program, my C library, but it actually doesn't have a memory address or anything for that. So this would just be a declaration for that variable, right? So you can declare it and just give it some of those attributes, and then in another file I can say int x, and then if I put a bracket 10 in C++, it'll actually allocate 10 chunks of memory for it, right? So they can have one spot where it's the actual definition, and another one where it is the declaration in a language like C and C++. And in fact, everything needs a declaration. Functions need declarations, and that's why C++ and C have header files. PHP, again, many of you have or will use PHP. Languages are actually embedded inside of HTML markup. The scope of a variable is local to a function, and if it's declared outside of a function, the scope lives from the declaration up until the end of the program, but you don't have access to that variable within within any of the other functions, right? So it's kind of a global scope that begins at the declaration. If you want to access a global variable, you need to use a special keyword global, or use this $globals away. I have to apologize, I don't use PHP, so I don't know PHP at all. So those of you who use PHP, I'd love to hear if you have anything interesting to elaborate on that. But they handle globals differently. Python actually does something similar to that. If you want to access a global variable, you could just put its declaration anywhere in the file, and it lives from where it's declared to the rest of the file. You can read from it in functions, but you can't write to it in functions. You can only write to it if you declare it within the function as being non-local or global, right? Otherwise, it's available for reading, but as soon as you write to it, you implicitly create a local version with the same name that shadows the original. So you have to use the word global to prevent that from happening. Okay. So static scoping, again, it's when the scope can be determined before you run the program. The issues with static scoping is that you can access every global variable, and you can access variables from any containing scope. A lot of times you can see stuff that you really shouldn't, the execution of your program shouldn't depend on, right? So even though there's like a bazillion global variables out there, I might reserve the right to get rid of one of them or change the meaning of one of them as I work on my program. And if you're writing some other piece of code that relies on that global variable, we've got a problem, right? So, and that's not just true for global variables, that's true when we end up having nested scopes and nested functions and things like Python, right? So this ability to see outside of your own innermost scope in order to find out what values are can give you too much access and cause a problem, which is what's summarized here, right? You know, the solution that people in large projects would tend to do is end up having too many global variables. Okay, so that's static scope. In practice, static scope is the right thing, right? Just don't use globals. And you've probably heard that quite a bit. There are like a few special cases where it's good to use globals, but in general, you should just try to avoid them, and if you have to use them, if you can, pass them in as parameters instead of accessing globals. If you find yourself in a situation where really the only practical thing to do is to use a global, document the heck out of it. Just make sure you're clear. It indicates long-range coupling in your program, and that can be a problem. Now, the original Lisp programming language was used a different type of scoping, which was it just crawled up the runtime stack in order to look for the variable, right? So the meaning of a variable didn't depend on the nesting depth of scopes in your source code. The meaning of a variable just depended on where I was at this runtime dynamic stack. So if I called a function maybe foo, and so foo was up here on the stack and it had x equals 3, and then foo called fizz, and maybe it had x equals 77, and then later I'm in bar and I want to say, hey, what's x? It's going to look up the stack and it's going to find this one, right? But later it could be the case that I call bar from something else. Maybe I've got some function Bing, and I say x equals something completely different, right? And then after Bing I call bar, and when I look up x from bar, because at runtime this is the previous declaration, it's going to find x equals ABC. So the issue here is you have no way when you're writing the code, right? Maybe bar was written at the global scope, right? I have no way to figure out I'm going to find for x, right? With static scoping, if I can't find it here, maybe we'll use curly braces, if I can't find it here, then I expect to find it here globally, right? Whereas with dynamic scoping, if I can't find it here, it depends on which other functions were called before bar was called. And that makes it really hard to figure it out. And of course, the next slide has an example, which I should have shown you before drawing pictures, right? So here you've got an example of you've got the function big. Within the function big, you've got x equals 3, right? Here you've got the function sub 1, and within sub 1, you've got x equals 7, and in sub 2, you have y equals x. And so the question is, if you invoke the function sub 2, what value does it find for x, right? So with static scoping, you can predict that, right? So the reference to x in sub 2, if you look at the containing scope, are we missing some curly braces somewhere? I can't tell where the curly braces are supposed to be. Oh, that's lovely. The containing scope, I think we would find this that x belongs to big X, right? It's going to be this one, x equals 3, right? If we use dynamic scoping, big calls sub 1, sub 1 calls sub 2 uses x. So sub 1 was called before, so it's going to look in sub 1 to find x, and it'll find this one, right? So you have to pay attention to that call sequence, right? So it finds sub 1s. This little example was an attempt to show the same thing that I wrote with the with the pen on the previous slide. So if you want to know whether something uses dynamic scoping versus static scoping, you have to think about, when I'm looking up a name which is not local, what scope contains the name? Is it the scope of the nested block in my source code, or is it determined by looking at a previous entry on the call stack, right? So does it use the stack to figure out the nesting scope, or does it use the nesting of these blocks in the parse tree, right? Is the scope determined by the parse tree, or is the scope determined by the runtime stack, right? If the scope is determined by the hierarchy of scopes that you might encounter on a parse tree, then it would be static scopes. If it's from the runtime stack, then it's going to be dynamic scoping, right? So there's pros and cons, right? It's convenient to recycle the stack. You have to maintain a stack in order to run the program anyway, so it's convenient just to be able to use that stack to look up variable names. And that's probably why it was done in Lisp, a very simple language, the original one. It was made more complicated for Scheme. Scheme, which we used, was using static scoping and not dynamic scoping, but the original Lisp would have used dynamic scoping. The disadvantages are extreme. When a subprogram is executing, all of its local variables, they're visible to every other program that executes after it. You can't do static type checking because you can't tell what the data type of a variable is going to be until you run the program, because it just happens to depend. Was the previous thing on the call stack setting x to a string, or was it setting x to an integer? You don't know. And it leads to poor readability, right? For the same reason that you can't statically type check, a human being, when it sees a variable that hasn't been declared anymore, a programmer who sees a variable name, one of the things they're going to say is, what's that? And they need to be able to figure out where they can look up, well, what is this thing? Is it a parameter? Is it getting passed in there? Is it a global variable? No. Who knows what it is? It just depends on what function was called first. And you have to understand all the different ways that the program might execute in order to have any sense of understanding what the meaning of a particular statement is going to be. So dynamic scoping is probably not very good, right? So again, scope and lifetime, remember the difference. Scope is about visibility. Lifetime is about occupying a memory cell, right? So you can be alive and be hiding, which means you're out of scope. A static variable in C++ or C has a lifetime that's the entire duration of the program, but it may not always be visible. Let me explain what that means. If you know C or C++, if you write void foo, and you write in here static int, it's supposed to be C int x. This x has a lifetime, maybe there's a curly brace, some more code. This variable static int x has a lifetime which is static. It lives for the entire time of your program's executing. But it's only visible in this scope. You can't see it out here, you can't see it out there. If you have some other function, void bar, you can't see it there either, right? It's only visible within this scope in which that static declaration was made, right? So that's a big difference between visibility and lifetime. Okay, so this is what they mean when they say a static variable in C or C++. Right? It gets remembered between consecutive function calls, but it's not visible outside of that function's block of code. So this is a little bit of foreshadowing, and I've been using this concept. I've used the term active to talk about. When we were looking at the stack, and I said you've got a stack pointer for some function, and you've got the variables that are local to that function that would be put on the stack as long as that function is active, right? What's actually happening is these are the local variables, but you're also going to have a pointer to the referencing environment, which in a statically scoped language, it likely lives somewhere on the stack, but it's not immediately above you, right? So you're going to have your local variables, and you're going to look there first to figure out where they are. If you can't find them locally, you're going to look in some other environment on the stack. And at the very top of the stack, you might have your globals, right? That's supposed to be a B, globals, right? So you might end up pointing up there, or you might have one function, so you might have more complicated scenarios where your referencing environment might need to be maintained by a garbage collector, and so it would be out here, right? But the idea here is you have these little sets of names and values that are being kept in hash tables, and so you've got your current scope of the active function plus pointers back to these reference frames or referencing environments, right, of all of your ancestors, right? So when we talk about a given statement, so once a statement executes, you've got the environment that's local, right? So all the names that are visible to that statement, right? So in a statically scoped language, it's the local variables plus all of the visible variables of the enclosing scopes, right? And so you have some pointers to those enclosing scopes. They may or may not be on the call stack. In a dynamically scoped language, you have, again, your referencing environment is your local scope, and if you can't find it on the local scope, you just look one step up the call stack, and you just keep scotching up the call stack, right? So it's much more simple, right? In a statically scoped language, if you don't find it locally, it becomes really tricky to figure out where I'm going to look to find my parent scopes. But in a dynamically scoped language, you just crawl up the call stack, right? Regardless, when we talk about a referencing environment, we're talking about this entire stack of hash tables, right? This entire sequence of environments of reference frames that you go through to try to figure out what the value of a particular variable is. Okay. Your referencing environment, another way to think about it, it's the set of all of the names that are visible at a particular line of code. So when you're looking at a line of code, you want to ask yourself, what are all of the variables that are visible? Not just the names, the variables, right? Because it's the name, it's the entire, you got multiple variables with the same name, but maybe only one of them is visible to you, right? So it's not just about names, it's about which variables are accessible at a given line of code. Another concept which is very similar to a variable is a named constant, right? It's bound to a variable let me read this properly here. Okay, so this first sentence of the slide is a little bit confusing. What it's trying to say is you can initialize it. Like, you can only bind it to a value at the same time that you elaborate the declaration, right? So once you put a value in it, you can never change it afterwards. So that would be a named constant, right? So it's immutable, right? So when they say the advantages of readability and mutability, the scenario where you'd use a named constant is, for instance, instead of saying 3 or 4, you can give a flag a meaning like orange or red or green or blue, right? So instead of having to write a color as a number, you can actually give it a human readable name is a named constant, right? You can use them to parameterize programs. So for instance, configuration. If you're going to do a machine learning algorithm and you want to set the learning rate, this is likely a setting that you want to be able to set once, but you don't want to dynamically be adjusting it later in the program. You still want to be able to trust that things don't change when you're not looking at them, right? So for instance, a thread safety could be an issue, right? So this idea that you can only write to it once, but once it's gotten a value, that is its value forever. Things that don't change can't cause deadlocks, they can't cause race conditions, or they won't, probably. They're less likely to. I'm trying to think about how they could, but I don't want to commit to that, right? So these named constants can give you some sort of semantically useful notion there. Now, you can either statically associate a value with a constant, and they call these manifest constants. And that would mean that the name gets this value sometime before runtime. And the beauty of this is that your compiler can actually go back and find and replace. Wherever you use the number, the name red, it can just paste in a 1 or a 2 or whatever the enumeration value for red would be. So an enumeration is a great example of a bunch of manifest constants, right? So those things, they're never going to change in your program. They let you write readable code because you're using words that mean something to us, but the compiler can, before it even runs, it can do a lot of optimization, it can inline them, etc. Another type of constant would be called a dynamic constant. This would be something like, in the example of a configuration file, you might need to read it in from a file at runtime, but then once you set it, you can never modify it again afterwards, right? So that would be a dynamic named constant. It's writable, but then it becomes immutable after it's written. Languages like C++ and Java have a way to do constants. The keyword const in C++ and final in Java would mark a thing as being a named constant. C# lets you use the terms read-only and const. It uses const for the manifest constants, and it uses read-only for dynamically bound constants. That kind of wraps up this chapter. We kind of hit everything in the outline that we're supposed to go through. Just a quick summary here. Case sensitivity and the relationship of special words are design issues related to the names of variables. Variables have those 6 attributes that you should all be able to rattle off: name, address, value, type, and then lifetime and scope are those kind of funky ones. The binding is the process of associating an attribute with an entity. Could be a variable, could be a function or something else. The book uses the term scalar variables. You might be more comfortable with the term primitive variables. They can either be static dynamic, and then there's two types of heap dynamic: explicit or implicit heap dynamic. You should be able to describe what each one of those are. The slides themselves didn't say strong typing, but the book does, and I think I alluded to it. So all of the discussion that we saw about types, and especially in a static type system, the intent there is by, especially in a static system, right? In order, if you can know the data types of all entities, then you can make sure that they're used in ways that are compatible between the types. So a strongly typed language means that every variable is going to have a type, and the compiler is going to be able to detect all errors associated with using the types incorrectly at compile time. Right? Different languages have different levels of strength in typing. A lot of languages have the ability to cast away the type or pretend that it, erase the type temporarily. Just because strong typing requires so much rigor and thought and planning of a programmer that we're not good enough to do it efficiently enough to get the code to market on time. So even within languages which have rich type systems, they may not necessarily qualify as strong. Ada was a very strongly typed language, and you don't see a lot of code written in Ada because it's hard to do. It's like the tangled web we weave when first we practice to create a strongly typed language. And that kind of wraps up the slide show. I want to, in this video, which is currently just under 2 hours, I want to talk about some examples of problems from the book that one might do, right? So again, it's always a good idea to look at the review problems. Define binding time. What are the 4 times bindings can take place? These are all 22 of these review problems are questions that I'm likely to ask you in some sort of quiz or exam. What's the purpose of a let construct in a functional language? You know what the purpose is, right? I mean, you can tell me that. Let me see here. I got a black screen. I need a different frame where I occupy the full frame. In fact, let me do that right now. Okay, I'm big. I was going to try to get rid of the green screen stuff, but it doesn't. I don't know how to make that work. So I got the book. I'm looking at problems, and I'm gonna actually look at the problem set of your book to get some inspiration here. This is where obviously your instructors go to get some idea of functions to look at, and I see a good one. Consider the following JavaScript skeletal program. You know what I'm going to do? I'm going to shrink myself and move myself off to the side, and I'm going to add a new video capture device, and I'm going to try to capture the Lumens document camera, which I have done. Here. Aha. Great. So, oh, it's covering me up. There we go. I'll just make it nice and big, and see if I can't try to work through a problem. But my document camera is way over here, so you won't be seeing me. You won't really be seeing me anyway unless I lean over. Okay, so if we look at the book, we have some problems, And I'm looking, for instance, at a JavaScript, at problem number 6. Consider the following JavaScript skeletal program, and I'm just going to write it down. We have the program looks like there, x, and then we have a function called sub1. And within sub1, we have there x, and then a function, a nested function, called sub2. And then it has something which we don't care what it is. And then we end this curly brace. So I'll just call that curly brace number 1 and that curly brace number 2. Alright? And finally, again, after that, we have another function called sub3 with its own curly brace, and I'll just put the word 3 above it, just so I can keep track of all of those little blocks. Okay. And the question further says that the execution is in the following order. Main calls sub1. Now when they say main, I am not a JavaScript programmer. Most of my JavaScript programs don't really have a main, so I'm not quite sure what they mean, but we're going to have to imagine that sort of the main execution flow calls sub1. Sub1 calls sub2, and then sub2 calls sub3. Alright, so the question is, let me just kind of draw that here. So the question is, assuming static scoping in the following, which declaration is the correct of x, is the correct one for a reference to x? Okay, let's see. So first we've got, you're in sub1. Inside of sub1, we're inside of sub1, which declaration of x? So we actually over here, let's give them names. Let's call this declaration 1, and I'll do it in green, and this one is declaration number 2. Okay? So it's going to be useful to us to number them. This is why, line numbers would be great. So those are the two different places that x was declared. So if we're in sub1, the correct declaration for x is going to be static scoping. Static scoping. The correct declaration for x has to be the local one, right? So it's going to be number 2. That would be true for static or dynamic scoping. If we're in sub2, okay, so if we're in sub2, by the way, pause the video and work through this. If we're in sub2, which one is it? So we're in sub2. Static scoping would mean, again, it's declaration 2. The trick here is none of this matters because we're doing static scoping, right? And if we're in sub3, this is part A. And if we're in sub3, then it's going to be declaration number 1. Part B, so part A is static scoping. Part B asks the same question, but with dynamic scoping. Okay, so I wish I hadn't crossed that out because now this matters. Okay, so let's look again. For sub1, when we're in sub1 and we're referencing x, it's still going to be declaration 2 because it's declared in sub1. When we're in sub2, here, well, let's look up here. Sub1 calls sub2. So if I look at the call stack here, all right, the way that it goes is, you've got sub3, sub2, sub1. I can't find it in sub2, and then you've got main. I can't find it in sub2, so I'm going to look up to sub1, and then I'll find it. Perfect. Okay. So far, no different. Sub2 calls sub3. Okay, so when we're in sub3, I'm looking for x, and I don't find it locally. So I can't find it locally. In dynamic scoping, I look at the next block up the call stack, which is actually up here in sub2, and I can't find it locally. So I continue up the call stack, and there I find it in sub1, and so again, that's the declaration number 2. Okay, so this is going to be the main declaration, and these are both the sub2 declarations, right? I think that that's the answer that they want. That would be the correct way to answer that. And these would all be these would be the sub1 declarations, and these would all be sub1s. Every single one of them would be sub1. So we can see that it was really different for part 3 of the problem. Okay, so this sort of question is one that you should expect. There's another question, number 7, which is very similar, and there's a question number 8, very similar, and a question number 9, also very similar. So we should be able to work those problems out. So what I want you to do is I want you to be ready in class in small groups so that we can work through the problems in the problem set that look like this problem, where you're given a piece of code and you're expected to, under these different types of scoping, explain where a declaration is. I'm also going to do problem number 9. So in problem number 9, we're looking at a Python program, and at the global scope we have x equals 1, y equals 3, and z equals 5. And then we define, this is defining a new function called sub1 in Python, and then the block of code is everything that's indented to the same level. So here our block of code says a equals 7, y equals 9. The sample code uses semicolons, but semicolons don't mean anything in a Python program unless you're interactive. And then some other stuff that we don't care about. At the same level of indentation, and I'm going to draw vertical lines to indicate the levels of indentation here, right? At the same level of indentation, we have def sub2, and in there we declare a variable with the keyword global x, and then we say a equals 13, x equals 15, w equals 17, and we have some more stuff. But then indented under sub2, we have another nested function. So this is just more miscellaneous stuff. We have another function, def sub3. You can do nested functions in Python. And here we say non-local a, and we say a equals 19, b equals 21, z equals 23, some other stuff here, maybe some other stuff here after it in sub2, and maybe some other stuff over there, we don't care, right? So this is the whole Python program, right? The question says, list all the variables along with the program units they are declared that are visible in the body of sub1, sub2, and sub3, assuming static scope is used. Okay, so static scope. That's the same scope Python normally uses. Okay, so we need to list all of the variables along with the units in which they're declared in, let's say, sub 1. Okay, so in sub 1, we can see x, which is declared at the top level, so it's global. We could use the word global there, right? And we've got y. Y was declared in sub 1, and so that's going to shadow the global one. So this is declared in sub 1. We've got z. The z was declared in sub 1, and so that's going to shadow the global one. Okay, and nothing else is visible inside of sub 1. So that's it. A is declared in sub 1. I almost missed that. So we have A, Y, Z, X. Okay, so 3 of them are from sub 1, and 2 of the global ones are shadowed, but the X from global shows through. The other thing says what's visible in sub 2. So sub 2, nothing in sub 1 is going to be visible. The containing scope is global. So in sub 2, even though we see ourselves assigning to x, it's still using the global x, right? So x is global. We have an A, which is going to be local to sub 2, because it doesn't exist globally. And we have a W, which doesn't exist globally, so that's also going to be in sub 2. But we also have access to the global Y and the global Z to read to them. The reason that X was declared globally was so that we could write to it without creating a new local variable. Okay? And if we look at sub 3, okay, here we're nested pretty deeply, so let's look at this. We have non-local A, so that means when we write to A, we are actually using the A. It's not in the global scope, but it's in a containing scope. So we're going to look up, and we're going to find A right here. So A was declared in sub 2. B is not global, and it's not in sub 2. You're writing to it. So B is going to be in sub 3. Z, we're writing to it in sub 3, so Z is also going to be in sub 3. And what else do we have access to? A is already used. X has not been shadowed, so we have X from sub 2. And we have W from sub 2. I'm sorry. X was declared global, so X from sub 2 is actually X global. And W from sub 2 is not global. Okay, is that everything? How about Y and Z? Z is from sub 3. Okay, so we still have access to Y, which is global. Okay, so how did I figure this out? This A is actually that one. This X declared global is actually that one. So for each thing here, I just first look through sub 3, A, B, and Z. I figure out where they're declared, right? Then I work my way up. A's already been handled. X was global, and then W, and then I work my way up. All right, we've already handled X. We've already got a Z. So what's left is the Y, which is global. Okay. So that's how you would answer question number 9, to list all the variables along with the program units in which they're defined using Python, and the global and non-local keywords to Python, which were described in the chapter and the slides. I'm going to stop recording right now, and we are right at 2 hours. Please watch this video. I'm going to work through exercises like this in small groups for class.